All right, well, here we are. This is Calculus 2. Of course, it's the follow-up to Calculus 1. So what we're going to do here is we're going to actually start by going over integration, which you should have seen some of this at least in Calc 1, but for the time being, we'll be reviewing integration concepts before we move on to more advanced topics. Because, of course, integration is one of the more complex topics and more important topics in calculus. So we want to understand what it is and how it works. And of course, we want to get a lot of practice with the different techniques that we need to solve for integrals whenever we may see them. So first of all, note that the integral of a function is something that we can calculate by taking the area under the curve that is associated with that function and calculating the area between two particular points or else across the entire real number line. You might remember that this is known as the fundamental theorem of calculus. And so you can see in this diagram here, I have the function f of x, which we don't know what it is, but for the purposes of this graph, you can see that curve represents f of x. And if I need to know the area under that curve between a and b, what I'm doing is taking the integral of f of x between the points a and d. So in other words, integrals correspond to areas under a curve. And in fact, the integral itself is nothing but an infinite sum. In fact, some have suggested that the sign for integration is itself simply a variation of the summation sign. I don't know if it's possible to determine if that's true or not, but you recall this is the Greek letter sigma, and it is often used to represent a sum. And so the integral sign you can see is sort of a curved version of it, where you can see what we're essentially doing here is an infinite sum. All right. Now, by the way, you might also recall that there are two basic types of integrals. When we don't have specified endpoints like that, we're just integrating over the entire real number line. This is called an indefinite integral. And then when we have two specific endpoints, this is known then as a definite integral, because here we're looking for a specific value. We're only interested in a certain part of the real number line. And when we're done, the result will be some constant. Whereas on this side, most likely we'll end up with a function of some kind, although it could be a constant. On this side, we're guaranteed to obtain a constant of some kind. All right, so we're going to take a quick step backwards and revisit our friend this summation notation, which I just mentioned. And again, I just want to remind you that this is the Greek letter sigma. Specifically, this is the upper case version of sigma. There are actually two you may have run across before. This one, you may have seen this as well, especially if you've taken statistics, this is the lowercase sigma. But of course, this one is also known as the summation operator. And when you see this, of course, it tells you you're going to add up something. The rules will be determined. You'll be given a function, and you'll be given an index of some kind, which will tell you how to proceed. But you're basically just adding up numbers. The sigma on the right, as you know, if you've had, like I said, had statistics, is the standard deviation. So let's take a look at a specific case. So what this is telling me to do is take whatever x is some variable, which is indexed by I, and the possible range of values for I is from 1 to n. So what this is basically doing is saying to do the following. That's all it is. It's that simple. Now, of course, we can have far more complicated cases. For example, the I doesn't have to start at 1. It also doesn't have to increase one at a time. You can actually have cases where the index is increasing by some other value besides 1, but 1 is the most common situation. The x itself, we can add up functions of x. For example, we could have x squared, whatever the case may be. And so just a quick example, imagine yourself looking at the temperatures observed in Minnesota during the first 5 days of January. So we have a sample here of 5 temperatures. And so when we apply the summation operator, what that's telling us to do is simply add up the 5 temperatures, and you can see that the sum is 10. Let's just quickly look at a couple of other cases. For example, here we have the sum of the squared x's. And what that's telling us to do is square each term before we add them up. So using the same data we had a minute ago, which was 2, -1, 3, 5, and 1. If you square each term separately and then add them up, you'll see that this time we get 40. You never know, depending what formulas you're working with, what kinds of functions of x you might need. Now, here's an interesting case. Although this looks superficially similar to what we just did, these are 2 very different cases. In the first case, what we're doing is summing the squared x's. In the second case, we're adding them up before we square the sum. So here what we're doing is we're squaring the summed x's. And you can see, at least in this case, it gives us a very different result, because this time we're adding up the numbers, which gives us 10 like we saw earlier. And when we square 10, we get, of course, 100. So these two are very different from each other. They're not going to equal each other, except by coincidence. Like, for example, if they're all zeros, of course, they would be the same. But most of the time, these two will give us very different results. You run into this case in statistics as well. What's happening here is that we're doing a few different things. We're taking each x in our sample, and then we subtract a constant k from each one before we square the terms, and then finally we add them up. Okay, so k can be any constant. So what you're figuring out here is the squared distances from each x with k. So using this, let's say the temperature data again, if for some reason we need to subtract 3 from each one, here's what would end up, and then square them, of course. This is what you'd end up with. So if you notice, what you're being told to do here is for each x, subtract the 3 first. Then you square the difference, and then you add them up. And of course, you see that we're getting 25. Now, these are specific cases, but we can define several key rules that will make it easier for us to deal with the summation operator. For example, if we have a sum of constants, let's say, for example, we're being told to add up 5. This is actually telling me to add up 5 3 times, which is, of course, going to equal 3 times 5, which is 15. And that's what this is telling us. All right, well, you don't run into that very often, but this is how the notation works. C, the sum of the c's is going to be equal to the number of c's that we have times c itself, and that will give us our final sum. Right, exactly, like this. Now, algebraically, when we have a constant like this, we can move outside the operator, so that, let's say, in the next slide, you can see we have the data that we had earlier with the Minnesota temperatures. And if I now want to add up 2x, you can do one of two things. You can double each term and then add them up. But what you could have also done is simply said, all right, if the sum of the x's is 10, then the sum of the 2x's is just 2 times the sum of the x's, which is 2 times 10, which is, of course, 20. By the way, I do want to point out, sometimes when we have I equals 1 to n, Sometimes in some books and in some places, you'll see that the index has been left out. It's implied then that we're adding up all the terms from 1 to n. If we need something else, of course, it has to be explicitly written there, but sometimes you'll notice that in some textbooks, they may not necessarily bother to put in the indexes, and sometimes it's not really necessary, but I prefer to always make it explicitly clear which indexes we're using. We also have algebraic properties that we can apply here. For example, the sum of a plus b, we're adding up each one individually. It would be the equivalent of just adding up all the a's and then adding up all the b's and adding them together. And then similarly, the same thing is true for subtraction. Now, here's where it gets interesting. You can actually take a sum and break it up into separate pieces. Sometimes it's very convenient to do it this way. Let's say, for example, something as simple as I equals 1 to n for a. Now we know that this means to take all the a's from 1 to n. Well, if you notice here, what we're doing is saying, all right, well, what we could do is break it up into two pieces. 1 to m and m plus 1 to n. Now, why might you want to do this? Because it may be that some of the terms have properties that are different than the other terms, or there's something significant about each individual group of terms that we want to capture or at least calculate before we add them up. So just it's important to be aware that you can take a sum like this and break it up into smaller components if there's a good reason for it. Now, here's some useful shortcut formulas, and this is very helpful for proofs. It turns out that some of these summations can be simplified very easily. Here's exactly let's take a look at this one. The sum of I equals 1 to n equals n times n plus 1 over 2. Okay, now we're not going to prove that here, but I mean, we could use an example. Suppose, for example, I had I equals 1 to 10. Okay, 1 through 10. What they're telling us here is that the sum is equal to 10 times 11 over 2, which is 55. Now, there's a clever way you can prove this, by the way. Well, at least not so much prove it, but demonstrate it. Let's do this. You can think of this as imagine yourself taking the first and the last terms and adding them up. And then you do the same thing here. And again, and of course, I've left out some of the middle ones, but the point of this is that altogether there are 5 pairs of numbers that add up to 11. And therefore, the sum must be 5 times 11, which is 55. So that's kind of the logic behind this formula. You're basically taking pairs and adding them together. So that's what this is all about. Now, you can do something similar with I squared. Now, of course, of necessity, the formula is a lot messier. Let me just quickly show you an example. I'll put this up here so you can see the formula again. So let's say we're adding up the squares of the first 5 terms. And you can see that if you do it manually, of course, you'll get 55. But following this formula, it's 5 times 6. Now, 2n plus 1 in this case would be 11. And it is 55. What do you know? All right. And there's others too. Like there's one for IQ. There's one for a lot of the standard formulas. This one is n squared, n plus 1 squared over 4. So let me put this up here to remind you. So yes, you can individually cube these terms and add them up. But let's see what would have happened if we use this formula. 5 squared, 5 plus 1 squared over 4. Oh no, sorry. Wait a minute. I just realized my mistake. Sorry, 36. God, no wonder. Okay. So yes, it's 225. Now, this is interesting. Look what you can do. And again, this could potentially come in handy if you have an unusually messy expression that you have to add. What's been happening here is that I minus 3 squared, you can multiply that out. You can use FOIL or whatever technique you want to use. O I and last. So that brings us to I squared minus 6i plus 9. And now if you notice, break it up into 3 separate terms. And all of these have a rule that we've seen. Okay. So, for example, and by the way, what you can also do here, you can then move this -6 outside. And now this is the one we've started with, the constant. We don't need to do anything with it, except to remember the rule. So the I squares will give us this term. And then, of course, the next one is -6 times the sum of the i's, which you recall is n plus 1 over 2. Okay, so the second term looks like this. And this is the formula for I squared, I, just plain I. And then for the constants, remember, and that's what we have here. And so we combine all 3 terms, and we end up with this enormous sum. Now, we can certainly confirm this, not by hand, of course, by going to Excel or something like that, but it's nice to know that we can break it up like this and treat each term separately, because I think you'll agree that that's a lot quicker than trying to do this directly, because there may not be a formula for us for I minus 3 squared, but we can certainly rearrange it algebraically to find something that we do know formulas for. Oh my God, now look at this disaster. But, oh, wait a minute. Look what we can do. We can break it up into the sum, the difference of I cubed minus I squared. We know each of those has its own formula. And so we should be all set. All right, there's the IQ squared formula rather. Here's the IQ formula. And we go through and evaluate them, and we do end up with 350. All right, so now let's get back to the integration. Now, of course, the purpose of doing all this is because if we're treating an integral as an infinite sum, it's good to know how the discrete sums work. So we start out by assuming that f of x is a continuous non-negative function, and it's defined over the interval a to b, including a and b's. So if you notice, by the way, I just want to remind you how this works. The notation, that is, when you have something like this, that does not include either a or b. You might remember some books, let me improve this drawing a little bit. What they do is they use the circles to indicate that this is not part of the interval. In other words, it's everything from a to b, not including either a or b. Whereas let's say you have this, now that's a different situation. A is not included, but b is. And then for this case, it's the other way around. A is included in the interval, but b is not. And then finally, the last possibility is that both A and B are included. This is often referred to as a closed interval. This is an open interval. And depending on what book you're using, this one is sometimes called semi-open. It actually, I guess, when you come right down to it, it could be either semi-open or semi-closed. I'm not sure which one the book prefers. Let's just check it out. Yeah, it doesn't really matter. All right, we'll call it semi-closed. How about that? It just means that one side is open and one is not. Okay, just in case you've forgotten how this notation works. So when we're looking at intervals like this, there's only four possibilities. It's open, closed, semi-open, semi-closed on the upper side and on the lower. Anyway, this is what this looks like. Now, if we wanted to know the area under this curve between A and B, area A is the integral of this function. Okay, according to the fundamental theorem of calculus, which we'll look at again later. Now, what we're going to do here is take a look at the logic behind this. So let's just say that we take this curve. We're basically going to break it up into intervals. What we're effectively doing is we're taking each of these. Okay, now this is not drawn as well as it could be, but the basic idea is that you're adding up these intervals, the areas of these intervals. And if you add up enough of these intervals, you'll end up with the correct sum, which is our interval. So we're going to imagine that the interval is broken up into this kind of thing. Now you can see there's going to be some approximation errors because we're trying to calculate the area under a smooth continuous curve with a series of rectangles, basically. But if you have enough of these rectangles, their widths will get progressively smaller, and in the limit, the area of all those rectangles will match the area under this curve. But there's a couple of ways we can do this. So here what we're saying is that this represents the difference between each of these x's. X minus the previous value of x. In other words, let's say this is x3 and this is 2. Then what we're going to be looking at, this is the width of that interval. And by the way, the intervals are chosen on purpose to make sure that the distance between each x is the same. Okay, we have to keep that in mind. So in other words, the widths of these rectangles are all the same. So it's b minus a over n, where n is the number of the intervals. Okay. So we're going to define delta x to be that constant width between the two. So in other words, let me try to draw this again. We're basically breaking this up. In this case, we have 1, 2, 3 intervals. So the width of each of these is b minus a over 3, because there's only 3 rectangles. Okay. And what it also implies is that for any x, let's say x2 is x1 plus the distance between the two. Oh, sorry, no, I'm looking at it wrong. X0 is the starting point. In other words, x2 is 2 intervals away from x0. That's what this is meant to represent. So now when we do this, we can think of intervals starting at the left endpoint, and then we can do the same thing for the right endpoint. And we're going to see that the two of them converge to each other. So we'll start with the left endpoint case. So now if you notice the way it's written, here I has to start at 1 so that for the starting point, this interval represents x0, x1. Okay. And then it goes up to n. When I equals n, then that means that we're looking at the interval okay, so that covers all of them. Okay. All right. So for each rectangle, we're going to have the same constant width, delta x, but the height will be this point. In other words, for the first interval, the height will be here. For the second interval, the height will be here. For the third interval, the height will be here. And for the last interval, it'll be here. So in other words, we could have done this on the right side. If we're doing the right endpoint approximation, the height would be here at x1, x2, and 3, etc. So the reason why it's called left point approximation is because we're measuring the height from the lower limit of this interval, the left endpoint, so to speak. Okay, so the sums of these rectangles rather will approximately equal the area under this curve. And as we shrink up the gap between the rectangles, in other words, as delta x converges to 0, the total area of the rectangles converges to the interval between A and B. And in addition, it doesn't matter if we use the left or the right endpoint approximations, they'll both converge to the same answer. What we basically want to show is that it works both ways. So with this formula, then see if I can do this. So the idea here is that this is the left endpoint. This is the height of that rectangle, and this is the width. And of course, as you recall, the area of any rectangle is the height times the width. So this represents what you're seeing here is the sum of the areas of all the triangles. They're calling it LN. L stands for left, by the way. N is the number of intervals. Okay. So that expression up there can be expressed more compactly as this. Okay, so what you're seeing is the sum of all the heights times the constant width. Okay, beautiful. Now, for a graph like this, there's no way I was going to be able to draw this myself. So I borrowed this from the book. And this is the left endpoint method. All right. Yeah. So my graphs were okay, but this is the real thing. So this is what it's supposed to look like. And you can see there is an approximation error here. We have some little gaps in here. But if we keep shrinking up the width of these, in other words, if the number of intervals keeps increasing, the widths have to decrease. In other words, instead of having 4 rectangles, what if I have like 4 million rectangles? You can imagine that they're going to get awfully, awfully close to that curve. So in the limit, as n goes to infinity, then the area under the curve will exactly match the area of the rectangles. Now, the difference between the left endpoint approximation and the right is, of course, that now the heights are coming from the right endpoints. So this, oh, hold on. Sometimes this tablet pen is a little annoying. God, this thing made a mess. I'm using a tablet. You can't see it, but I'm using a tablet, and I don't know. It can be incredibly annoying. I don't even know how that got there. I'll tell you what. Let me do this. I've never seen it before. It's doing that on every slide. Whoops. Hold on one second. All right, it looks like we're safe here. Yeah, I mean, it was making a mess. If there's this pen, if you hit the wrong button, it can make all kinds of problems. Okay. So let me just show you the graph. So you can see now the heights are coming, and you notice that in this particular example, when we use the left endpoint method, the rectangles for the most part were under the curve. We were underestimating the true area. When we use the right endpoints, we're actually overestimating because the heights are being taken from the right endpoints. But that's why, again, if you do this with enough rectangles, you should get the correct answer, but you also will find that the areas with the right and the left endpoints will get closer and closer to each other, and eventually they will converge to the correct value. So here is a bunch of calculations. I think we'll kind of skip over this for now. Maybe we can revisit this tomorrow, but this is a very specific example where you've got x squared over 2 over the interval of 0 to 3, and delta x is 0.5. And you can go through and confirm with your calculator that the sum does, in fact, add up to 3.4375 from the left and 5.6875 from the right. So you can see right now there's a huge gap between the two, and you can see why. The one on the left is significantly underestimating the area under that curve. The one on the right is significantly overestimating it. So the only solution to this is to continue to increase the number of intervals. Now, of course, that increases the computational time, but what integration is really all about is making all this unnecessary by giving us formulas that we can use to avoid all of this. But it's important to see what we're actually doing when we integrate, to really understand what the process is all about. Now, we're going to introduce a very important concept called Riemann sums. And what's different here is that we're not restricted to the left and the right endpoints any longer. We can essentially pick any point, for example, the midpoint. And we may find that we find our solution quicker than if we're using the left or the right endpoint methods. Now, obviously, Riemann is named after the mathematician Riemann. He had a lot of contributions, including finding a way. Yeah, he had this thing called this sphere. I remember seeing this Riemann sphere, which gets us involved with imaginary numbers. It's basically a way of visualizing complex numbers, but it allows us to divide by 0 somehow. But anyway, all right, so we don't have to go over that right now. So let's say that we arbitrarily pick some point, like the midpoint, to be the height of our rectangle. So we'll call that x star. Now, we don't need a left and a right version of this. We're just picking some in-between point. And so you can see that what's going to end up happening, we're still just calculating the height times the width. And the width is never going to be, it's going to be the same every time. Here's the height, here's the width. Now, you'll recall from Calc 1 we learned about limits. And what this means is that as the number of rectangles increases and converges to infinity, that means each individual rectangle is getting much smaller. The widths are getting smaller. And so you can imagine that if instead of approximating a curve with just a few rectangles, oh, that's not good. Hold on. All right, well, you get the idea. Instead, what you're essentially doing is you're going to wind up with an infinite number of these lines, each of which has a width of 0. Now, the definite integral simply means that we're restricting the range of the interval, or the integral rather, to a specific range of values between A and B. So that means we're going to end up with a very specific constant when we do this. Okay. Now, if it's possible to do this, and it's not always possible, remember, we assumed earlier that the function is smooth and continuous. If there are any discontinuities in the function, it may not be possible to even define an integral in the first place. But assuming we're dealing with well-behaved functions, smooth continuous functions, this is what we mean by the definite integral. Now, and see, that's what it's telling us here. If f of x is continuous over that interval, it doesn't have to be continuous over the whole function, but over that interval, then we are guaranteed that there will be an integral over that interval. Okay, that's all it takes. Okay, it's discontinuities that can cause problems. Now, here they're going to use the Riemann sum to come up with the approximation of this integral. So let's just say that the integral are, oh, by the way, we know what this function looks like, so let's draw a picture of it. Now, delta x is 2 over n, where n is the number of rectangles that we're defining. And therefore, no matter where we are, each xi, as we saw this earlier, is equal to 2i over n. Okay, so let's say we have let's keep it simple. All right, so x1 is x0 plus then 1 delta x. Delta x would, of course, therefore be 1. So x1 would be 0 plus 1. Okay, or two times I is 1, n is 2, so you just end up with 1. Now, we saw earlier that xi equals 2i over n. That implies that xi squared is 2i over n squared. And then that gives us okay. Remember we said it here that delta x is 2 over n. Okay, now we should be able to solve for this using the techniques we had earlier. Let's try that. Okay. So what they've done is multiply these out, 8i squared over n cubed. Now, n is a constant. Remember that. So that means we can factor these out. Now, the sum of I squared, we had earlier, Okay, let's go revisit it. Let's go find it. There we go. So, oh, it is on the next page. Okay. So therefore, wow, what a mess. So when you multiply that out, you can break it up into these three terms with a bunch of algebra. We skipped over that. This is what you end up. Now it's broken up this way for convenience, as you can see, because remember, what we said earlier was that this integral is the limit as n goes to infinity of the widths of the bars times their heights. We just got through proving that this expression is here. So now we're basically taking the limit 8/3 plus 4 over n plus 6n squared. Now, of course, as you recall from Calc 1, if n goes to infinity, this term goes to 0 and this term goes to 0. Because you have a constant over infinity and that's equal to 0. So we end up with 8/3. So what this is saying then is that for this particular example, this equals 8/3. Now, between the two methods, of course, you would have learned in Calc 1 a technique for dealing with this type of integration. If you've forgotten, so in our case, this is actually definite integral. So instead of having a constant, you're going to have x cubed over 3 evaluated from 0 to 2, which means 2 cubed over 3 minus 0 cubed over 3, which is 8/3. Okay. So, this means we can just confirm that we've done this correctly using the technique of Riemann sums. Of course, once you've understood what the Riemann sum is telling us, we don't need to keep doing it this way. It's you can learn the integration techniques that some of which we've already seen, and then do it directly. But it's useful to know how this is obtained. In other words, we're using a technique which we really should understand what's going on behind the scenes. So let's see. I didn't open up. Here we go. So I broke up the chapter, by the way, into multiple parts because I'm not sure how far we can get in each session. And these are pretty long chapters. I find that it's easier to break them up into little pieces. Oops. Okay. Also, I'm going to post these slides that I've been writing on, so you have both the original slides and these as well. In other words, if you look at Moodle, you'll see that these notes are already there. but the writing that I'm adding now is not there. So I'm going to save these. And so both versions will become available on Moodle. Okay. So then definite integrals, of course, are the ones we're interested in coming up with the integral over a specific interval on the real number line. And so you can see sometimes the areas are positive, sometimes they would technically be negative, depending on where the function goes. So yeah, this is what we're basically doing with our Riemann sums. Okay, so in other words, you have to take into account that you've got two different areas. One is positive, one is negative. So this is what the definite integral is about. You're taking the difference between two areas. Okay. And the difference between them is the area that you're looking for. All right. So it's sometimes called the net signed area, meaning that we're taking into account the signs. If you didn't do that, well, all right, let's see how this works. So you've got f of x equals 2x, so it's a straight line, but we're looking at the interval from -3 to +3. So in other words, the area underneath this curve, if you notice, to the right of the horizontal vertical axis, we're interested in the area underneath the curve, and to the left of that, we're interested in the area above the curve. So the integral will be the difference between these two. Okay. So let's see. Well, these are nice and easy because they are triangles. You can see A1, we calculate as the area of the triangle 1/2 base times height. So the way this is described here, the base is 3. The height is 6. So that A1 triangle has an area of 9. Over here, let's see, the base is 3. The height is actually -6, but because it's under the line, but we're going to call that +6. And so the two of them have the same area. So the grand total is 0 because we're taking A1 minus A2, which is 9 minus 9, which is 0. Now, integrating, by the way, let's go back and do this again the traditional way with the rules. I'll move the x on the outside here. So you've got 2 times 2's cancel each other out. So the total area under that in that range is defined as 0 because the two triangles exactly offset each other. The triangle on the left is defined to have an area, technically it's -9. Although, you know, I mean, in the plane that we have here, you can't actually have a negative area, but we're defining it as negative because it's under the horizontal axis. A1 is +9, they're both 9. 9 minus 9 is 0. Okay, so for any integrable function over the interval a to b, closed interval, We have A1 and A2. The net signed area is A1 minus A2. And the total area, not the net signed area, but the total area would therefore be 18. Okay. So we have some rules that we need to know about definite integrals. Here you can see this is a strange case because the lower and upper limit are the same. This is defined to be 0. Why is that? Because we have a straight line here, and the base of this line is defined to be 0. It's actually a line segment. The base is 0. The height is whatever this thing is. The height is f of a. So the area is 0 times f of a, which is just 0. Now, this opens up the doors to some algebraic properties that we could use. And you can see here, interestingly enough, if we reverse these two, that makes the area negative. Now, this one is pretty self-explanatory. The integral of a sum is the sum of the integrals. And the same thing is true for the difference. The integral of a difference equals the difference of the integrals. Constants can be moved to the outside of the integral sign. Now, here's something else that's just like, remember before we saw that with a sum, we can break it up into two individual pieces. Well, the same thing is going to hold here. Okay, because we have let's say this is A, B, and this is C. So what they're basically telling us here is that the total sum from A to B consists of this sum plus this sum. And that's what they've done is they've broken up into two pieces. And yes, I've shown down here below how it is comparable to what we did before with these summation signs. All right, so I'll tell you what, since it's the first day, we'll knock it off right here. So what I'm going to do here is I'm going to take each chapter and break it up into individual pieces. I'm aiming for an hour at a time. In other words, I want to have 1 hour modules, so to speak. And so this is chapter 1, and it'll probably require 4 or 5 parts to cover the whole thing. So when this video is stored on YouTube, it'll be listed as chapter 1, part 1. And the next one will be chapter 1, part 2, etc. So it'll be easy to find what you need when you go back to look at the videos. So this way, you know which one is which, what order they're in, and I mean, we could go by dates, I suppose, but I think it's easier this way, so that the titles specifically tell you what section of each chapter we're in, so that by the time the week is over, we've covered some entire block of material, possibly one chapter. I don't think we have enough chapters for one chapter per week. So it might end up being more like one chapter every 2 weeks, but we'll see how that goes. The important thing is that this video will be organized so that it's broken up into 1 hour pieces, so that each chapter is essentially a section of its own separate videos. So tomorrow, I'll be releasing the second part of this, where we just pick it up here from slide 26. We'll carry on from there. And then by the time the week is over, we should be through chapter 1, I suppose, and maybe starting chapter 2. We'll play that by ear to a certain degree, because we do have 8 weeks. And I can't predict exactly how long it'll take to get through each chapter, but I just want to let you know. And also, don't forget, this is going to be stored in YouTube. not Moodle, because apparently Moodle has space constrictions that I don't know why, but YouTube has plenty of space. So, all right, so we'll stop here and we'll pick it up tomorrow, which is Monday the 5th, with part 2. Okay, so good night.